Okay, good. Now, let's start. Now, so this is we are now in week 5. So in week 5, I'll be teaching you phase diagram. Okay, phase diagram, which is one of the important topics in engineering materials, and also a little bit complicated than all the topics. Okay, this is a little bit complicated, but rest assured, I will give you the best way for you to overcome this. Okay, once you master phase diagram, the way you see the phase diagram will be completely different than before. All right, so phase diagram is a little bit complicated, but there's a way for you to understand those, because phase diagram is packed with a lot of information in one diagram. Imagine you have two components in a system, two components in a metal. For example, brass, you have zinc and copper. Within these two components, you have composition. 0% of copper, 100% of zinc. 0% of zinc, 100% of copper. So you can see there are about 100 points of material that can exist. So within these 100 points of existence, what is the influence of temperature? What is the influence of pressure to the microstructure? That is what phase diagram is. So from it. So it is a bit complicated, but don't worry, let's go through one by one. Okay, now phase diagrams, there are few, before I start the lecture, there are few definitions and basic concepts that you need to understand. The definition, okay, you need to memorize those definitions, and I'll be going through one by one with you. Now, components are pure metals and or compounds which an alloy is composed. So you have pure metals or compounds. That is component. We call that components. Okay, components can be pure metals or compound. Okay, so if you are studying pure metals, there will be only one material exist in the phase diagram. If you are studying components, if you look at the phase diagram, there will be two material in your, what do you call that, x-axis, horizontal line. Okay, for example, copper and nickel. Can you see this? Copper and nickel. Okay, I will explain to you this in a while. So this is where the composition will be on the phase diagram. Okay, and let's talk about solvent and solute. Okay, solvent, the keyword for solvent is mole. Let's say, okay, let's look at the definition. Solvent is the element or compound that is present in the greatest amount. Okay, the keyword is mole. Okay, greatest amount. Solvent atoms are the host atoms. For example, you have water and you are adding sugar into it. Water is your solvent. Sugar is your solute. Okay, you can put a remark. So water is your solvent. Sugar is your solute. Solute is an elemental or compound present in a minor concentration. So sugar is in minor concentration. You are adding salt. You are adding sugar into a water, and it becomes syrup. Okay, sugar water. All right. Now system. Am I recording this? Okay, good. All right. System is a specific body of material under consideration. So system is, for this topic, we look into examples. That is system. All right. The series of possible alloy consisting of the same component but without regard to alloy composition. Okay, we are looking into components. For example, over here, where is it here? Components. All right. But without regards of alloy composition, for example, iron carbon systems, copper zinc systems, and so on. Okay. Now next, solubility limit. Okay, now let's look at this phase diagram. This is also one of phase diagram, unary phase diagram. All right. Solubility limit is a maximum concentration of solute atoms that may dissolve in the solvent to form a solid solution. Okay, I'm repeating this again. Solubility limit is a maximum concentration of solute atoms that may dissolve in the solvent to form a solid solution. Addition of solute in excess of these solubility limits results in the formation of another solid solution or compound that has a distinct different composition. So what are they trying to say over here? It's very simple. Look at your phase diagram. In phase diagram, you have two components. One is water and another one is sugar. Okay, one is water and another one is sugar. And here it's stated that composition, weight percentage of sugar. Now everyone look at your x-axis, right? Horizontal line. Here 0, it means that you have 0 weight percentage of sugar. A lot of students make mistakes. They say that here 0 is 0 content of water. No. Look at the title of your x-axis. It says composition weight percentage of sugar. So 0 here means 0 weight percentage of sugar, which equals to 100 weight percentage of water. Here the water is 100%. Okay. I'm repeating. Here the water is 100%. Here the sugar is 0%. As you move further on the x-axis, you have 20. It means that 20 weight percentage of sugar having 80 weight percentage of water. Here is 80. Two composition you mix up together, you get 1 fraction of 1, which is equal to 100%. That's what I'm trying to say. Here, composition of sugar is 40%. Composition of water is 60%, and so on. Okay. All right. Having said that, so this is your solubility limit in your phase diagram. Okay, this is your solubility limit. So solubility limit says that this is the maximum concentration of solute atoms that may dissolve in the solvent to form a solid solution. All right, now let's say now you have a temperature of 20 degrees, a water temperature of 20 degrees, and you have a liquid solution which is an addition of sugar and water. So this is sugar and water. All right. So at first, the water is 100%. You add sugar. Of sugar. At one time, you can't add more sugar liquid solution. When you keep on adding more sugar, the sugar doesn't dissolve in water. That is what solubility limit is all about. At 20 degrees Celsius, the solubility limit for liquid, Silap solution is around, let's say we put it at 63 weight percentage. It means that in 100 grams of water, 63 grams of sugar is reaching its solubility limit. When you add more sugar, after that, those sugar cannot dissolve into the water. So you have two types of what they call that phase in that system, which is liquid solution and solid sugars. Sugars doesn't dissolve. I'm talking about 20 degrees Celsius. Let's say you heat up those solution to 80 degrees Celsius. Supposedly, the solubility limit at 20 degrees Celsius is 63, but now it becomes 75. Then you can add more sugar into the solution without having two different distinguish of phases until it reach the solubility limit until here. Then it have two types of what they call phase. Can you understand until now, guys? This is the basic. Can you understand? Okay, so the simple ones. All right, good. So now, I told you here we have one phase. Here we have one phase. Here we have two phase, right? So what is phase? A phase is a homogeneous portion of a system that has a uniform physical and chemical characteristic. Okay. A system composed of two or more phases, we call that as heterogeneous system. So all the compounds in this world are heterogeneous. Pure is homogeneous. A mixture of two compounds is heterogeneous. And microstructure, you know what is microstructure is now, okay? In metals, alloy microstructure is characterized by the number of phase presence. So microstructure is the one that is governing the mechanical properties of a material. Okay, guys, microstructure is very important. Microstructure is the one that is governing the mechanical properties of a material. So in metals, alloys, microstructure is characterized by the number of phases present. For example, martensite, ferrite, pearlite, and so on. Their proportion and the manner in which they are distributed or arranged depending on the alloying elements present. Okay, it depends on the alloying element present, their concentrations, and also the heat treatment capabilities, heating time, rate of cooling, and so on, which we have discussed previously. Okay, microstructure. Now, phase equilibria. Phase equilibria means that, okay, when you look at phase equilibria, the keyword that I'm looking into is minimum energy. It means that a material is in stable state, minimum energy level. Remember previous lecture, minimum energy level, steady state. So that is what we call phase equilibria. Is a system is at equilibrium if its free energy is at minimum. Okay, free energy is entropy and enthalpy. Is at minimum under some specific combination of temperature, pressure, and composition. Okay, under a specific combination of temperature, pressure, and composition. And it refers to the equilibrium as it applies to a system in which more than one phase may exist. Okay, it is also applicable to more than one phase. Phase equilibrium is reflected by a constancy with time in the phase characteristic system. In your phase diagram, the constant unit is time. Okay, in your phase diagram, the constant unit is time. But phase equilibria won't happen. I mean, it is all theory and pure. Most of the time, it is metastable state. We are in a metastable state, non-equilibrium. Okay, it is often the case, especially in solid solution, that a state of equilibrium is never completely achieved because the rate of approach to equilibrium is extremely slow. Okay, for example, undercooling. You need to have vast amount of undercooling for you to have phase equilibrium or equilibrium state. So because of that, such system is said to be in a non-equilibrium or metastable state. Most of the systems are in non-equilibrium or metastable state. And a metastable state or microstructure may persist indefinitely, experiencing only extreme slight and almost imperceptible changes as in time progress. Often metastable structures are more practical significance than in equilibrium ones. So all the materials, all the systems are in metastable state. So when there is a slight change in temperature, pressure, or composition, you will have some reaction. Okay, you will have some reaction as the time progress. Okay. All right. Next. Okay, the control of microstructure or phase structure of a particular alloy system is conveniently and concisely displayed in what is called as phase diagram. Okay, that is what phase diagram is all about. The control of microstructure or phase structure of a particular alloy system is conveniently and concisely displayed in what is called as a phase diagram, equilibrium or constitutional diagram. And in phase diagram, the three main parameters that affects phase structures are temperature, pressure, and composition. Highlight this. Three main parameters that affects the phase structure is temperature, pressure, and composition. Okay. Okay. Phase diagram. Phase diagram is the represents of phase present in metal at different condition. For example, temperature, pressure, and composition. Okay, I already said here temperature, pressure, and composition. So phase diagram is the represents of phases. Okay, phases presence in metal at different condition. It indicates the equilibrium, solid solubility of one element in another. It shows the equilibrium value. It also indicates the temperature range under which solidification occurs. At what temperature does the solidification occurs? Phase diagram also indicates the temperature at which different phase starts to melt. See, so many information a one phase diagram will give. Okay, so take your time, try to digest. Okay, now let's see, what is this? This is for single pure substance. Okay, pure substance exists as solid, liquid, and vapor. Okay, now you know that phase exists in three different phase exists in three different realms. We call that as liquid, solid, liquid, and gases. Okay, and this phase between solid, liquid, and gases is being separated by a phase boundary. We call that phase boundary lines. These are the phase boundaries. Okay, these are the phase boundaries. Okay, let's look at water, and this is pure ion. Okay, here, if you look at the temperature, here is 0, and here is 100. Okay, and this is the pressure. At 0 degree, below 0 degrees Celsius, at pressure of 760 mercury mm, water will become solid. So it is being represented in the phase diagram. All right. After 0 degrees Celsius, where let's say you are in a room temperature at normal 1 atm, water is in liquid. At 100 degrees Celsius, at 1 atm atmospheric pressure, water will start to vaporize. So this region is vapor. This region is, we call that liquid. This region, everything is solid. Okay. This region is vapor. This region is liquid, and this is solid. And these three distinct phases is being separated by the phase boundaries. So all these phase boundaries will meet each other at one point. We call that as triple point. So the triple point for water is 0.01, where three different phase exhibit equilibrium in three different what they call realm, which is solid, liquid, and gas. They coexist in three different phase, which is solid, liquid, and vapor. So if you can manage to reduce the pressure, if you have a vacuum chamber, if you can manage to reduce the pressure into, don't know how many atm, I mean pressure low that, of course, definitely lower than 1 atm, because this is 1 atm, and you reduce the temperature to 0.01, water exists in vapor, water exists in liquid, water exists in solid. Okay, same goes to this is ferrum. Okay, iron. All right, so iron, you have triple points here. Okay, here it means that an ion can exist in solid, alpha particles, and also vapor at this line. And iron can be in gamma particles, which is solid, gamma particles in solid, and also vapor over here. And here, at this pressure and this temperature, a solid can be in beta particle, which is in liquid, solid, and also vapor. These are the triple points. Okay, so this is liquid line. Okay, guys. Hold on. Okay, we have a question. Are we using torr units in pressure? Yes, yes. I mean, depends. You can change to mm per Hg or torr. Torr is the absolute pressure based on. It's a unit of pressure based on absolute scale. All right. We can use torr. We can use mm per Hg. We can use atm. It's up to you. I mean, they will show in the phase diagram what units they have been using. It can be either degrees Celsius, it can be also Fahrenheit or Kelvin. There's lots of things of units. Okay, not Thor the hammer. That is different. Okay. Not this guy. I learned to use GIF in what they call that, Microsoft Teams. Okay, guys. All right, now next, let's go to this Gibbs phase rule. Okay, so having said that, we have three different phases that coexist, that can be coexist, and also three different phases which is being separated by the phase boundaries. We have one rule, we call that as Gibbs phase rule. So Gibbs phase rule actually computes the number of phases that can coexist in equilibrium of a chosen system, and then it calculates the degree of freedom, which is which is F, the degree of freedoms where a material is being dependent on when they want to change phase from one to another. So this is the formula, very simple formula. P plus F is equal to C plus 2. So P is the number of phases that coexist in the system. For example, in water, you have three phases, 1, 2, 3. So for water, you have three phases. And there is one component in the water of the system, number of components, C is component. So in this phase diagram, but how many components? We have only water. We have how many phases? We have three phases. So phase is 3, component is 1. Therefore, 3 plus F is equals to 1 plus 2. So F is equals to 0. So number of degree of freedom is 0. So the degree of freedom indicates the number of variables. Okay, how many numbers of variables that can be changed without changing the number of phases. So if you are in one phase, what are the variables that can change? For example, the variables will be temperature or pressure and so on, or components. Okay. Now let's look deep into phase diagram. In phase diagram, we can have a binary alloy and also a mixture of two system or metals, and also two component systems. Okay. There's a term word isomorphous system. Okay, there's a term, it sounds isomorphous system. It means that any two components, okay, any two components or elements that is completely soluble in each other in liquid and in solid state. For example, alloys, brass, water, syrup, and so on. This is completely soluble to each other in liquid and solid state. Okay, for example, copper nickel solutions. Okay, you have here copper nickel solutions, and let's see what they are trying to depict here. Composition at liquid and solid phase at any temperature can be determined by drawing a tie line. Okay, from here on, guys, I'll be showing you the shortcut. Okay, you can see it's very complicated, right? All these blah blah blah, a lot of things. Okay, I will show you the shortcut of interpreting the phase diagram. Okay, now you need to listen to me very carefully. All right. So this is your phase diagram, and here temperature is given in degrees Celsius, and here weight percentage and nickel. Okay, always student make mistakes in the x-axis. Here it means 0 weight percentage of nickel, and here 100 weight percentage of nickel. It means 0 weight percentage of copper, 100 weight percentage of copper. I'm repeating again. Huh? Here you have a phase diagram. It says weight percentage nickel, 0 weight percentage nickel. So all over here 0 weight percentage nickel. All over here is 10 weight percentage of nickel until 100 weight percentage of nickel, which is pure nickel. This is pure copper. In other words, okay, this is pure nickel, right? Here it will be pure copper because here copper is 100%. Here 50-50. Okay, here 50-50. Can't draw a straight line. Okay. Now, composition at liquid and solid phase at any temperature can be determined by drawing a tie line. Okay, for example, there's a question. It says that the weight percentage of a system consists of 53 weight percentage of nickel. So you have a system consists of 53 weight percentage of nickel. So this is 10, 20, 30, 40, 50, 51, 52, 53. So 53 weight percentage of nickel is here at the temperature of 1300 degrees Celsius. So the question say you have a solution, and the system is at 1300 degrees Celsius, having a composition of 53 weight percentage of nickel. What is the phase for each solid and liquid presence in that solution? So how are you going to do it? So we're going to start analyzing by drawing a tie line. We call that as a tie line. Okay, now at this composition and temperature, the phase diagram exists in liquid and alpha is solid. Okay, in solid alpha particle or solutions. We call that here. So this is all solid line. This is all in liquid. Here everything is solid. Here everything is in liquid. Between these two, solid and liquid, you have a small composition over here where liquid and solid exist in both phase. Okay, so where liquid and solid exist in both phase. Okay. Let's say the solutions, the question says, what will be the composition of solid phase and liquid phase when I have 53 weight percentage of nickel at 1300 degrees Celsius? So you draw a point here. Let me zoom. So you need to draw a tie line. A tie line is a horizontal line which starts from the origin of your system and it touches the liquidus line. So here we call that as liquidus line. And also this line we call that as solidus line. Liquidus line means liquid line. Solidus line means solid governing line. So you need to draw a tie line, this and this. So you have a solid nickel of 58 weight percentage. You have a liquid composition of nickel at 45 weight percentage. Okay, first step, draw the point, draw a tie line which is horizontal, stop when you're hitting the liquidus line or solid line, and then draw a vertical line saying that what is the weight percentage of liquid for liquidus line, what is the weight percentage of solid at the solidus line. Okay, can you understand until now? Guys, can you understand? Okay, good. So three informations are available. The three informations. So it means I have 58 weight percentage of solid. Yes, here you have 58 weight percentage of alpha solid and 45 weight percentage of nickel, which is in liquid. The composition of it. Usually, will the temperature be given to find? Yes, of course. Sometimes you need to find the temperature as well. They give you the composition, they ask to find the temperature, and so on. Okay. All right. The three informations are available: the phase that are present, the composition of these phases, and the percentage or fraction of these phases. Okay. Determination of phase composition. All right, it should be here. Composition, it should be here. All these what they call the description, all these PDF description is being shown here. Okay, guys, what I'll do, I'll give you a break for 5 minutes, try to digest, and then we start to determine the phase composition and also phase amount. So usually in phase diagram, most of the question here will ask you to find the phase composition and also phase amounts. Okay, which there is some skills for you to draw it. Okay, I'll teach you one by one. So before that, it's going to be a little bit complex. So I'm going to give you a break for 5 minutes, try to digest, try to recall back, and then we start at 2:45. Okay. Yes, Lua Wenzheng. 45 and 58 is more than 100%. I'm talking about phase composition, not the phase, what they call that amounts. 45 and 58 is phase composition. Phase amount should be 100%. Don't get confused on that. Don't get confused on that.
So what is the difference between those two?
Okay, the thought is here. Lua Wenzheng, I'm confused on those two. Okay, don't worry. I'll explain to you on the phase composition and also phase amount in this slide. Okay. Meanwhile, you can just read and I'll explain to you on details at 2:45. Okay, guys, it's 2:45. Let's continue. Okay, now over here, guys, over here. So you have your phase composition and also phase amount. So there's one student who was asking me about Lua Wen Zheng, phase composition and phase amount. Okay, here, if you look at here, at this temperature, 1300 degrees Celsius, and at the initial, what they call the composition of 53 weight percentage of nickel, that material exists in liquid and solid. Okay, liquid and alpha solid, right? Let me clear this off. Okay, that material, the system consists of liquid and solid. So liquid and solid, they exist in correlation between each other. So what will be the percentage of liquid? What will be the percentage of solid? Okay, so the liquid percentage is 45 weight percentage, and the solid will be 58 weight percentage. But it doesn't state what is the phase amount. How much does the liquid present here? How much does the solid present here? So when you're talking about 1 gram of this, how many grams are presented in liquid? How many grams are presented in solid? So that the summation of these two will be 1, which is 100%. So that is what phase amount, how much. Phase composition, what type is being presented in this system. Okay, that how much is 100%, but what type can be anything. Okay, can you understand Lua Wen Zheng? Okay, no problem. Someone raise hand. Who is that? Laying Wing Zhou. Any other question, guys? Any other questions? Any other questions? Okay, I assume there's no question. Yeah, Yap Ching Peng. Anything? Oh, Yap Ching Peng trying to raise hand. Yap, who is the guy's name? Try to recall. Yap Ching Peng. Yap Ching Ping. Yeah. Oh, it's very difficult for me to pronounce your name, guys. Yap Chin Ping. Any questions? Oh, okay. All right. Okay, so let's continue. So determination of phase composition. Okay, I'll just read these glancely. Okay, not necessary. If you don't understand, don't worry. Okay, I will show you how to do it. I'll show you how to do it. Okay, so here they say that a tie line is constructed across two phase region at temperature of the alloy. The intersection of the tie line and phase boundaries on other side are noted. Perpendicular are dropped from this intersection to the horizontal composition axis from which the composition of each of the respective phase are. It's so boring, right? And I'm guessing a lot of you don't understand as well. I also don't understand. It sounds boring. And also for the phase amount, let's see. A tie line is constructed across two blah blah blah. Okay, the overall alloy composition is located on the tie line. Okay, this is important. The fraction of phase 1 is computed by taking the length of tie line from overall alloy composition to phase boundary for the other phase and dividing by the total tie line length. Okay, don't worry. The fraction of other phase is determined in the same manner, blah blah blah. If the phase percentage desired, each phase fraction is multiplied by 100. Okay, if you want to change to percentage, you times with multiply by 100. If you want to stay as fraction, it is just in a point form, which is equivalent to 1. When the composition axis is scaled in weight percentage, the phase fraction is computed using the Lever rule, mass fraction, the mass or weight, divided by the total alloy mass. The mass of each phase is computed from the product of each fraction and the total alloy mass. Got so many words. Okay, so I just read this without explaining to you anything. Okay, because this is a bit the way they construct the word is a bit complicated, but let me show you. Okay, this is the map for this topic 5. Okay, this is a map for this topic 5. We are somewhere around here. All right. Binary system, we have a few types of equilibrium phase diagram. The first one is binary isomorphous system. We have another type of phase diagram which is binary eutactic system, and we have another one which is equilibrium diagram having intermediate phase or compounds. Okay, 3 types of phase binary systems, right? Nothing much, nothing great. So I'm going to concentrate on binary isomorphous system and binary eutactic system for today. Okay, at first we look into this binary isomorphous system. So this is binary isomorphous system, and let's see what I can interpret here. Okay, if you look at this slide number 16. Okay, if you look at this slide number 16, this is a phase diagram for copper, nickel phase diagram. Here, 0 weight percentage of nickel. Here, this line, 100 weight percentage of nickel. Here, 0 weight percentage of copper, 100 weight percentage of copper. Okay, here is pure copper, here is pure nickel. Over here is all solid solution. Over here is all liquid solution. And this is your liquidus line. This is your solidus line. Okay, and this is the melting point for copper, where the liquidus line and solidus line meet. So this is the melting point for copper. Okay, copper here solid, right? This is solid. When you increase the temperature from 0 to 1084, it becomes liquid. Here, melting point for nickel is this 1455. You increase the temperature from 0. If you have pure nickel, you increase the temperature, it is still solid. Until this point, it becomes liquid. Okay, see, from here you have interpreting a lot of information. Now here, determine the composition here. This is just a zoom image of this. We have liquidus line, which is here. We erase all. So this is liquidus line, and this is solidus line. So liquidus line is the line that separates liquid and solid. Mixture of alpha, which is solid and liquid, separates. Solidus line is the line that separates solid and liquid. Mixture of alpha and solid and liquid and solid. Okay. So for example, remember this tie line. Okay, there was a boring description over here, this and this. Okay, so now listen to me carefully. Okay, I'm going to teach you how to find the phase composition and also the phase amounts. Okay, at first, for example, they have given you, okay, example. So this is the question. At 1250, an alloy having a composition of C0. Okay, so this is C0. Okay, let's say this is 34. Okay, an alloy having a composition of 34 weight percentage of nickel at 1250 degrees Celsius. So what you do is then, okay, you make a remark on the phase diagram. Look at what composition does this example coating. Let's say the composition is a liquid. It is very simple. Everything is in liquid. The whole system is at liquid. For example, let's say I pose you this question at 1300 degrees Celsius. An alloy with composition of 63 weight percentage of nickel. What will be the phase? What is the answer? At 1300 degrees Celsius, at 65 weight percentage of composition. So the alloy exists in this line. So it is in liquid phase only. It's easy, right? So you said 100% liquid. Okay, as another example, at 1200 degrees Celsius, I'm giving you another question. At 1200 degrees Celsius, an alloy with a composition of 45. What is the phase? At 1200 degrees Celsius, an alloy with a composition of 45 is here. 1245 is here. What will be the phase? The phase is solid alpha. 100% solid alpha. That's all. Problem comes when the question asks you, for example, the question that you're looking at it right now. At 1250 degrees Celsius, an alloy with a composition of 33. What is the composition? So you draw a line here. So here, the system exists in liquid and also solid. The system exists in liquid and also solid. So what is the composition of liquid? What is the composition of solid? So to do that, you need to use a tie line. Okay, you need to use a tie line. So tie line, you need to draw a horizontal line that touches the liquidus line and also the solidus line. Okay, guys, if you have a piece of paper with you, just try to draw. Okay, then you can understand better. So once you draw a line along the horizontal space, once you touch the liquidus line and solidus line, draw a vertical line pointing directly towards the composition axis, like this. Okay, draw a line directing to the composition axis. So here, when you draw a line, this means that this is the composition of the liquidus line. Here, you draw a line straight. This is the composition of the solid, CS. So you need to find at this present temperature and the given composition, we have a composition of liquid at this weight percentage and a composition of solid at this weight percentage. Now, how to determine the phase weight fraction? Okay, we are talking about the phase amount now. Okay, to find the phase weight fraction, which is the amount of phase presented in the system, we need to use the lever rule. Okay, lever rule is very simple. Okay, just look at this, guys. Just look at this. I will explain to you in detail. All right. These and this. Okay, just look at this. I mean, this is just a description. I'll explain to you. Okay, don't worry. Okay, step by step. So here you can find the composition of liquid. Here you can find the composition of solid. Now let's say if they ask you to find the weight fraction or phase amount. All right. So here with the given composition at 1250 degrees Celsius, if you want to find the weight percentage of solid, which is here, solid, this is solid, right? Solidus line, this is liquidus line. You need to use the lever rule. So the step is like this, R divided by RS. Okay. it means that if you want to find the phase weight fraction at this line, R, which is here, the difference between CL and CO divided by the difference between the whole region. Okay, I'm repeating again. Let's look at the weight fraction for solid. If they ask you to find the phase amount of solid, this, the difference between this divided by the difference between this, R and S. So what is the value of this R? R is CO minus CL. CO minus CL. And then what is the value of this and this? R plus S, which is CS minus CL. CS minus CL. Same goes to liquid, which is here. This is liquidous line. So you want to find the phase amount of liquid, you take S divided by R plus S. You take S divided by R plus S. Okay, so S is CS minus CO, which is this. Then CS minus CL, which is this. Okay, so the shortcut is, if they want to find the solid, you take the opposite of your lever rule. This is how you balance out R divided by R plus S. If you want to find the phase amount of liquid, which is here, you take the solid S divided by R plus S. S divided by R plus S. Here means this divided by the whole thing. Here means this divided by the whole thing, which is S divided by the whole thing. Okay, guys, do you understand this? Can you understand? Any questions on this? This is how you find the phase amount and the phase. Simple, right? Anyone don't understand? Yes, easy. Okay, good. Anyone else? I don't know why the equation. Oh yeah. That's the reason why I wanted you to don't look at the equation. You'll get confused. So I take the trouble to skip all these things and just show you this. Can you understand? I don't know why the equation is like this. Don't look at the equation. Just recall back what I've teach. Then you can forget about the equation. So how to know where's the CO? Okay, see, they'll give in the question, the composition. They'll give in the system. They'll give in the question. For example, in your tutorial, I'll give that in the tutorial. I'll tell you, okay, this is the composition, this is the temperature. Find the weight fraction, find the weight percentage, composition, and so on. So you need to draw a lever rule and start calculating. Okay. All right. Yo Xing Yuan, can you understand? Or do you want me to repeat? Yo Xing Yuan, you want me to repeat or how? You want me to understand? You want me to, do you understand or do you want me to repeat? Okay, good. Okay. So guys, so that is the essence of how to use the lever rule. Okay. All right. Now equilibrium cooling. Now let's look at the microstructure changes of what happens during cooling. All right. Now here an alloy with a composition of 35 weight percentage nickel. So this is nickel. 35 weight percentage is here, which is equals to 65 weight percentage of copper. This is copper. This is 65. Nickel. Always look at nickel, because since the x-axis says nickel, percentage composition of nickel is 35 here. So they say that at first in a liquid state, the nickel percentage is 35. We have only one phase exists, right, which is liquid phase. In liquid phase, it is in 35 weight percentage of nickel. All right. Then at from 1300 degrees Celsius, I'm giving you some examples, some scenarios, so try to imagine. I cool down this point A to reach point B. Okay, I cool down point A to reach point B, which is roughly around 1280 degrees Celsius. Okay, let's put it 1280 degrees Celsius. At this point, the whole system, which is liquid, suddenly have a new grain, which is solids, alpha solids. And this solid having a weight percentage amounting of this line over here, which is 46. 46 is growing. Okay. And then I cool it further. I cool it the temperature. I'm reducing the temperature from 1280 to say 1250. It reaches here. At this point, the microstructure looks something like this. Something like this. All right. You have a growth in alpha solids, 43 weight percentage of nickel, and a liquid having a composition of, you draw another tie line here at 32. 32. Okay. Then down the road, I cool further until the material reaches point D. Here, this is almost solid. Okay, almost solid. So you can see the solid alpha is growing bigger and bigger. The liquid having a composition of 24 weight percentage. And the alpha is stayed at 35 because it is in the solidus line. So, okay. Solidus line. Here, 35. And I cool it further to less than 1200 degrees Celsius, which is at point E. If you look at the microstructure, there is no liquid. It is all alpha 35 weight percentage of nickel. Okay, this and this can be correlated. Exists in one phase, which is liquid at 35 weight percentage. Here, solid at 35 weight percentage of nickel. Okay, this is how the microstructure changes. Growth here, it grows bigger, and it becomes solid. So the liquidus line diminishes. Okay. So just a quick bits on microstructure development. The mechanical properties in isomorphous alloy. When the composition of nickel increases in copper system, so this is pure copper, pure nickel. When the composition increases, when the nickel composition increases in copper system, copper as a solvent, the tensile strength increases until 60 weight percentage. After that, the tensile strength reduces because here it has reached its percolation threshold. Okay, same goes to elongation. The material becomes less ductile, more brittle, and then more ductile. Solid solution generating for single phase with a constant gain. So all this data is being done by the reference book. If you have the reference book, if you scroll down to appendix or glossary, appendix, not glossary. In appendix, you can view a lot of data for all these isomorphous alloys. And now we have the next one is a binary eutectic system. Okay, so until now we have studied on this what they call that isomorphous system, binary as isomorphous system. Okay, we have liquid, we have solid, and this can be correlated in exists in both ways. But now when we go into a mixture of two components which cannot really correlate into each other, we have the binary eutectic system, which is very similar to this, just that your lines is a bit different. Okay. Here you go, binary eutectic system, which is this. So in some binary alloy system, components have limited solubility, so it can't solute 100%, like in where is it? Like in isomorphous system, like this. All right. For example, the components for this example is lead, tin, or silver, copper alloys. So eutectic, there's a term eutectic, composition freezes at lower temperature than all other compositions. So eutectic is, we can call that as a triple point, in a phase diagram. Okay, let me show you. Okay, this, we call that as invariant points. So this is your eutectic temperature at these lines. Okay, below this line, majority of them are solids, this mixture. Here, alpha dominant solids. Here, beta dominant solids. Before we go further in this, let's finish this thing. Okay, this is the lowest temperature, is called eutectic temperature. Okay, over here, lowest temperature, eutectic temperature. So eutectic temperature, irreversible from liquid to cooling and from solid to liquid, which is heating. So from liquid to cooling, you have a solution of alpha, you have a solid solution of beta. From solid, you have a solid solution of alpha and beta, which through heating, you will get liquid, which is this over here, liquid. So in that liquid, you have alpha as well, and you have beta as well. Okay, all these are due to the components having a limited solid solubility. So you have different phases, which is solid in alpha phases, solid in beta phases. Okay, so let's look at the phase diagram for binary eutectic system over here. Tin lead. Okay, tin lead. When I was studying, we call that a sternum and plumbum, because I studied in Bahasa Malaysia, sternum and plumbum. So if you look at this phase diagram, here the same thing, guys. At your x-axis, the composition is in this is tin, sternum. Okay, I used to call this as sternum, so I get confused a lot. Okay, so this, the composition, sternum is tin. Okay, composition here is tin, 0% of tin, 100% of tin. Okay, here 100% of lead, 0% of lead. From this, you should know that alpha solid is rich with tin. Here, beta solid is rich with tin. I'm repeating this again. Here, alpha solid is rich with tin, is rich with solid lead over here. Here, beta solid, which is rich with tin. Okay. And this is the liquidous line that separates liquid and solid. This is the solidus line that separates rich lead particles and liquid. This is the solvus line that separates pure, which is rich lead alpha, and solid mixture of lead and also tin, alpha and beta. So this is solid. Sorry, this line is solid. This is also solid. This is also solid. Here, a liquid that is rich with lead, here a liquid which is rich with tin. This only one composition which is liquid, usually at higher degree Celsius. Okay. 327 is the melting temperature for lead. 232 is the melting temperature for tin. Okay, where your liquidus line and solidus line meet, that is the melting temperature, because here, this is pure lead, this is pure tin. See, so many information, guys, so many information. Can you follow me, guys? Can you follow me? Any questions until now? Okay, good. I'm being very cautious with this because a lot of information. Okay, so this is your invariant point eutectic system, and this is the composition for your invariant point, which is 18.3 here for alpha, and beta, which is 97.8 over here, and this is the temperature, eutectic temperature, liquid, alpha and liquid, beta and liquid, alpha and beta and solid, almost pure or rich in lead solid, almost pure or rich in tin solid, which is beta. Okay. Okay, another example for silver and copper. Okay, so please, you can interpret this. So this is copper, mean this whole line showing, sorry, this is silver, this whole line showing concentration of silver. So this is 100% silver, pure copper. And this is your eutectic, what they call that, composition for copper, eutectic composition for beta, which is silver. This is your triple point composition of eutectic, Ce, and this is the eutectic temperature, Te. Solidus line, liquidus line. That's all. Okay. So having said that, all right, this is the 18.3 in slide 25. 18.3 in slide 25. Okay, what is your question? Referring to lead is the maximum alpha phase. Lead, yes, maximum alpha phase at temperature. That is the triple point for that temperature. We call that as eutectic lines. These are the eutectic lines. So in eutectic lines at this temperature 183, this is the maximum phase that what they call that lead can occur in solid before it changes to liquid. Okay. At that temperature, Nur Harpinder. Okay, good. All right, here. Now let's go to one by one. Okay, liquid. So this is liquid. Stannum, which is tin, and plumbum, which is lead, mix homogeneously with some degree of flowability because this is pure liquid. Okay, it is almost homogeneously. So you have only one phase, which is liquid. There's no any distinct phase separation. Here, it is still liquid, but you have a distinct separation of phase. Okay, now look at alpha, which is this alpha. Alpha, which is this alpha. Here, this line, this line is solid tin with small amount of lead distributed homogeneously within the solid here. Okay, solid tin, this is solid, almost pure what they call that, stannum. Okay, pure stannum, pure tin, where lead is a little bit distributed. You have few weight percentage of lead here homogeneously within the solid. Beta, in other hand, beta is solid lead with small amount of tin distributed homogeneously within the solids. Solid and liquid presence in the equilibrium state here. Beta and liquid, solid beta and liquid present in equilibrium state here. Alpha and beta, solid alpha and beta present in equilibrium state. That's all. Okay. So remember the lever rule, as I mentioned to you in this. Same thing applies here. Okay, same thing applies here. For example, at 250 degrees Celsius, an alloy with a composition of C0, a tie line must be constructed so that you have liquidus line and solidus line, and find the composition of liquidus line and also the solidus line. So here's more of a beta governance. Here is more of a alpha governance. So the intersection, phase boundaries on either side. So you have a composition on liquid, beta rich. Here, a composition of solid, which is beta rich. Okay, so weight percentage for beta, you have to find the phase composition, the phase amount, sorry, the phase amount, weight composition of beta. Here, use the lever rule. So here, this is R, okay, C0 minus CL, which is this, divided by the whole R and S, which is CS minus CL here. If you want to find the weight percentage or weight phase amount of liquid, which is here, you need to take S, which is CS minus CO, CS minus CO, divided by the whole system, which is CS minus CL, which is this. Okay. Same goes to this line. Okay. At 200 degrees Celsius, an alloy with a composition of C0, let's say this is your C0 alloy. You draw a tie line and you just draw here. And the weight percentage, for example, if you want to find the weight percentage of alpha, which is here dominant here, you need to take R, which is CL minus C0, okay, CL minus C0, divided by CL minus CS, CL minus CS. And then if you want to take the composition of liquid over here, you need to take S, which is C0 minus CS, C0 minus CS, divided by the whole composition, which is CL minus CS. Okay, this is lever rule. Okay, if you want to find here, use S. If you want to find here, use R. Lever rule is a balancing rule. Okay. And then eutectic reaction. So sometimes the composition here is perfectly aligned to the eutectic point. Or we call that as an invariant point. So this liquid, okay, if you heat up composition, for example, this is 39 weight percentage of lead. You heat up to temperature of 150, 160 to above 170, and it changes directly to liquid, homogeneous, without going to the phase of this or this. Okay, liquid, alpha beta cooling, alpha beta from solid you heat up is liquid heating. So this is from here to here is cooling, from here to here is heating. If you go through the eutectic point, let's say your composition is perfectly aligned to the eutectic point. R and S stands for, frankly speaking, I don't know what is R and S, because I don't know, you can name it whatever you want, just a notation. Yeah. Lever rule, maybe you can Google it on lever rule. Let me see that. That's an interesting question. I never thought of what is R and L before. rule. Let's see. That's an interesting question. Okay, Google also doesn't find the answer. Can anyone shed me a light for this? Okay, Chin Wai look. I never thought of it actually. I just follow the rules of thumb, you know. Or you can just name it whatever you want. It doesn't matter actually. Okay, Chin Wai look. Okay, same goes to another example. Okay, we look at another example at 150 degrees Celsius and allow you the composition of this. 150 degrees Celsius is below your eutectic temperature. So everything is in solid, guys. Below eutectic temperature, everything is in solid. So it exists in either alpha or beta. See, it's either alpha or beta. C alpha or C beta. So if you want to calculate this, let's say if you want to find weight percentage of predominantly beta, you take R, which is here C naught minus C alpha divided by the whole system, which is C beta minus C alpha over here. Here, okay, this is a spelling mistake. If you want to find weight percentage of alpha, this is not L, this is alpha. Okay, alpha, you take S, which is composition of beta minus composition of your origin composition divided by composition of beta minus Ca. Oh, I need to edit this. I'm gonna edit some other times. Okay. Can you understand until now? Okay, there's another question. I'm more curious why they do notation or solid phase only, not liquid. Because liquid exists in correlation. Okay, you have more energy and it exists in correlation. But for solid, you have two different phase separating alpha phase and also beta phase because it exists as two different types of material. In liquid, both have been mixed together. So there is, you can have a relation between liquid when the temperature goes higher. For example, you can have those. Okay, for example, here's liquid. You can find the notations for alpha and also here you don't have. So it means that B have been totally diminished because the melting temperature for B for lead is here. For example, okay, here I can show you here. So it is above the melting temperature. So in this region, you can't find the phase amount for tin because it is way above the temperature or melting temperature for, so everything have been melted. Okay, but for, if you look at in liquid phase, if you want to find the composition amount of alpha solids, you can, it's over here. Okay, that's the reason why. Okay, almost done. Okay. So if you look into microstructure analysis, for example, in this binary eutectic reaction, here we are in liquid form, okay, liquid solution. For example, the composition 1 has a certain weight percentage of stannum, tin, so it is pure liquid form. Once I cool down from this temperature, let's say 350 degrees Celsius to 320 degrees Celsius, it touches in a region of alpha, which is rich in, I don't know, let's say lead, okay, alpha rich in lead. So you have alpha particles being grown. Okay, and there is still liquid composition, which is depict yellow over here. This is all liquid. and you cools down further, it becomes pure solid, where you have a grain boundaries between alpha grains. Okay, for example, I'm talking about almost pure lead, okay, with a very less weight percentage of tin. Let's say there is a certain amount or higher amount of tin. So this depicts on point D, okay, higher amount of tin when compared to composition of tin in this figure over here. Here, when I cool down from this temperature to region E, this liquid, you have the alpha particle first. Yes, it is almost similar with here. Okay, and then I cools further, it becomes alpha particle solid, which is very similar. And I cools further down, you have another new phase, which is beta particle due to the extensive amount of tin being used. So this is the beta particles in solid form. Okay. What is the interest in finding alpha and beta composition in solid mixture when you already know the composition of tin and it? This is important for heat treatment. Okay, you want to find at what temperature does heat treatment can occur, because all these changes the microstructure of a material. And I mentioned to you, microstructure is the important criteria to determine the mechanical properties of a material. So at what temperature, at what pressure do you want to heat treat an element? So that's the reason why most of it involve metals. So that is the interest. You need to find the alpha and beta composition. Okay, Chin Wai Look. Okay, now, so on your questions, now let's look at if you have a composition of 61.9. Okay, see if you have a composition of tin at 61.9, it is directly hitting the eutectic point, which is the invariant point. At liquid around this temperature, we are talking about what, 250 degrees Celsius, everything is liquid. And when it cools down, it touches the triple point. And when it cools down further, you have a combination of alpha at 18.3 weight percentage and a combination of beta at 97.8 weight percentage of solids. So if you look at the microstructure here, it is more uniform. Okay, it is more uniform, and this might have a better mechanical properties because it doesn't go through the alpha liquid phase or beta liquid phase. It changes from liquid directly to alpha and beta solid without going through the liquid phase over here. So the microstructure here looks like more of a, you can have a more crystals in this. Crystal means perfectly aligned shape orientation, which results in better mechanical properties. So that is the reason why here. So you have lead and tin overlapping each other. Formation of eutectic structures. So this is eutectic point, eutectic structure, and if you look under microscope, it looks perfectly crystal. Alternating layer of lead-rich alpha phase, solid solution dark layers, and tin-rich beta phase, and solid solution light layers. Very interesting, actually, if you look at phase diagram. Okay. Now, if you look at microstructure development without going through the eutectic point, for example, you have liquid lines, pure liquid with a composition of 40, and when you cool down, you have alpha rich liquid. All right, K, alpha rich liquid. And then when you cool down further, you have an alpha at 18.3 over here, and it grows bigger. So these have cooled first. Can you imagine these have cooled first? So if you look on a plane view, okay, if you look on a plane view, So these orange color particles have cooled first and created a grain structure, which is alpha rich, which is lead rich. So this liquid will tend to cool further when you reduce the temperature from L to M. So these have been cooled first. Can you see this? So that's the reason why we call that as prima alpha. And then you cool further, which is under the range of alpha and beta, you have the eutectic structure. Eutectic alpha, which is 18.3, eutectic beta, which is 97.8. So by looking at these, you might have a thought that this mustn't have a better mechanical properties due to the crystalline structure arrangement is not ordered. This is more ordered and so on. Okay. So along the Y line is always yes. Yes. Which denotes 18.5 stellium is the maximum can occur in alloy. Yes. So that is how you design the percentage of a material in a metal. Okay, guys. So far clear? Oh yeah, one more slide. Lead tin alloy composition of 50 weight percentage titanium, 50 weight percentage plumbum. Okay, so you can see the primary rich alpha particles, which is lead, and then you have the eutectic particles, which is lead and also tin, overlaps each other, dark and white. Okay, for slide 46 to the end, I will start discussing these on this coming Friday. Okay, which is more on the understanding, more of a theory based. Okay, what is ferrite, what is austenite, what is cementite, what is ferrite, and so on. Okay, guys. Any questions until now?
Sir, so the solid is always 18.3%.
Yes, the answer is yes. 18.5 is the maximum tin can occur at that line, which is the eutectic line.
So no matter how I draw, it's always 18.3%, is it?
Any questions, guys? Any other questions? Can you hear me? Hello? Okay, good. Yes. No matter how you draw, it is still 18.3. That is the properties of the phase diagram. Okay. So this is the line. So where is it? Yeah, this is the properties. Where is it? Okay, we call that a binary eutectic system, eutectic temperature. You are referring to the eutectic temperature. So this is always fixed, 18.3 and 97.8. This is the eutectic temperature at 183 degrees Celsius. Yes, at this eutectic temperature, the composition remains fixed at 18.3 for alpha, and the composition remains fixed at 97.8 at 183 degrees Celsius. Okay. All right, guys, any other questions from your side? Okay, guys, any other questions? So below the eutatic line, the composition will be different. Yes, if let's say this is your composition over here, your alpha rich composition and beta rich composition constructed in these tie lines, and also these tie lines, which differs a bit from these tie lines. Okay, can you see the difference between 97.8 and maybe here, somewhere around here? Not much of a difference for beta, but a bit significant difference for the alpha. Okay. All right, guys. So we have less students, 45 students only. "52 has voted. Some of you are missing in the class. Okay, I can't trace you. Yeah. Okay, Lua Wenzeng. Try to digest. If you have question, you can always text me, and also once I give you the tutorial question, you can understand better on that on those things. Okay, no problem. Okay, guys, any other questions? Any other questions? So those who haven't signed the attendance, please sign the attendance. Yes. Practical lab. Anything on practical lab? Clement, what is your question? Let me stop the recording.